Hello, everyone. Good afternoon. And so today actually will be our last lecture for this semester. We're gonna go through two parts. First, we will talk about some of the clustering algorithms that are left from our last lecture. We have covered k-means, right, and the mixture of Gaussian model, but we didn't. We skipped the ones in the middle. We skipped the. There are two cluster algorithms. The spectrum one, and the not spectrum, but the hierarchical clustering, but and the DBSCAN one. Okay, so we'll see how the clustering, the two different clustering algorithms can overcome the downside of k-means. Okay, and then after the clustering is done, we will use the rest of our time today to give a brief introduction lecture to the generative adversarial networks. It will be a very brief and gentle introduction to such a new technique. It's basically about the history of that line of work and about the state of the art and some technical information, some technical insight into the very first implementation of GANs, but not very too much details about the most of the state of the art work. Okay. So yeah, that is a plan for today, and so for the final exams, we actually will have it on next Tuesday, on May the 11th. So I will make the next Thursdays. So this week, Thursday this week, an optional lecture. Actually, you can come and we can talk about the final exams. And I haven't finished the slides, so I wanted to prepare some slides that as a guidance for you, how you get prepared for the final exam, how you prepare for the exam. So, but I haven't finished that slide yet, so I'm not going to talk about the final today, but we can talk about it next on Tuesday, on Thursday. All right. Yeah, that's pretty much the plan for today. Let me start sharing the slide for the clustering algorithms. Okay, so yeah, this is where we skipped the. No, not the final. No, the final will not be on Thursday. Final will be on next Tuesday. Yeah. Yeah, 3:30 to 5:30. Okay. So let's go back to the disadvantages of k-means, right? So we have talked about this a little bit. It's like if you have circles or non-convex shapes like this, basically the algorithm is not able to cluster the data points into the same shape that you are expecting, okay? Because the k-means algorithm is based on distance. It's based on how far away each data points are from the centroid point, okay? But it's not considered connectivity. Like it doesn't connect. It doesn't consider that for example, the inner circle, the inner ring, because all the data points here are connected, kind of connected to each other, but it's not recognized Okay, and also the non-convex shapes like this is also like properly clustered. So let's look at what the connectivity-based algorithm, clustering algorithm, can achieve. So the first one that we talk about is the hierarchical clustering. So the idea behind is that it's like the nearby data points will end up in the same cluster. Okay, so it's kind of a connectivity considered in this case. So the algorithm will use some data structure to implement the collection of clusters. It will initialize a cluster of singleton clusters. And that term means that we will basically assign each data points into one cluster. Okay, we will first consider each data point as a single cluster. Okay, and we will repeat the following steps. Okay, the first step is to find a pair of clusters that is closest in terms of distance among all the clusters available. Okay, so this argmin is to find the I and j that minimize the distance measurement. The capital D is kind of some sort of distance metric. Okay, it could be the Euclidean distance or whatever distance metrics that you wish to use. Okay, and the second step is to merge the two clusters into a new cluster. Okay, right, because they are closest. The Ci and the Cj are closest, so they will be merged into a new cluster. And next, we will remove Ci and Cj from the collection and add the new cluster into the collection. Right, that is very quite intuitive method. Okay, and the results of this procedure of this algorithm will produce a plots or a chart that is called a dendrogram. It's kind of a tree-like plots, okay, which basically shows the hierarchical tree of all the clusters in the graph. Okay, so in this case, we need to define a distance metric. Okay. All right, let's use an example to show how the algorithm works. Imagine the points here from A to N, right? We have that many points, which you think we can plot into a two-dimensional space, all right? So the clustering patterns seems not that observable, okay? And we will see how the hierarchical clustering will return. So because the first step is to find the closest sets, closest clusters. And in this case, because A and B, they are closest towards each other, so they will be merged into a same set. And the next one will be C and D. All right. So as you can see, after each iteration is done, we are connecting the two clusters that have been just merged, right? And you can see the second iteration has a little bit higher bar than the second one because we are growing a tree-like structure based on the iteration that the merging occurs. Okay. All right. So after C and D is merged, the next one it would be K and G, for example. Okay, so we should connect K and G together. The next one will be L and M. Okay, and the next one will be B and D. Okay, so this B and D connected together, which means we are connecting two clusters, and each cluster contains more than one data points. So we should work on top of these already merged clusters by connecting them together. All right. The next one will be from J to H, okay? And the next one will be A and E, right? and I and j, and k and I, m and n, ln, right? Until we reach the point that we have connected all the data points in the data sets. Okay, so and that is the first step down. We have created such a hierarchical tree plot, which is called a dendrogram. Okay. Yeah. Yeah, sorry, I missed the comments here, right? Thanks for the answering though. Yeah, so we will start not from a arbitrarily selected clusters, but we will treat each data point as an individual cluster. Okay, and we are now first conduct these steps of merging clusters together based on their distance, and we create this dendrogram, and this is our first step down. And the next step, we will need to work on top of this dendrogram and decide how many clusters we should split. Okay, so now we are done. So after the complete dendrogram is plotted, we can now use some threshold to split the results of the dendrogram into several clusters. Okay, so for example, if we could choose to use this red dash line as threshold, use this which corresponds to some distance. Okay, and we remove all the connections that are above this threshold. Okay, so that means that if the distance is above the threshold, we should not consider them as one cluster. Okay, we will only consider the data points that are below, that are within this distance threshold as one clusters. So if we look at below the threshold line, we can see that A, B, C, D, E, they actually belongs to one cluster, and the G, H, I, J, K, they also belong to one cluster, and L, M, N, and the F alone is one cluster, right? Because if we compute the distance from F to the distance towards its left, it will be already above the threshold. Okay, all right, so the results of setting this threshold is that we need to remove some of these connected lines in the 2D plot, right? So we need to remove those connections, and the clustering results will be like this. Okay, so only the distance, only the the data points that's only the clusters that are satisfy this distance threshold will be the ones returned by the algorithm. Okay, so according to this particular threshold, there will be 4 clusters returned by the algorithm. Okay. As you can see, there are a lot of flexibility here. The determination of threshold determines, like you can determine it by your observation, and you can try several different values, right? So if on the same example, we can of course use different threshold. Okay. So like if we use a little bit higher threshold, right? We moved up the threshold a bit up. So in this case, we have a higher threshold, which means we have a higher tolerance in terms of the distance. So we basically included the F into the cluster to the left, right? So we will consider this one as a cluster. All right. So it's a pretty flexible results. And if we lower the threshold, and we should remove more connections, more connected the edges. Okay, right? That means there will be more clusters left because we have a very low threshold now. Okay. All right. This is a complete example of hierarchical clustering, and you can see that there are a lot of places in this algorithm that we can tune, we can play around with. For example, the ways that we select the distances, the way that we define the distances, right? How do we decide the distance? How do we define distance between two clusters when there are multiple data points in both clusters? Okay, so like we can try to find the closest pairs of data points, or the farthest, or the average of all pairs, right? So different methods comes with different cost. If you want to measure the average distance, then of course there will be more computation needs to be conducted, right? So these are all trade-offs, okay? And they will also influence how the clustering results look like. Okay, so among the same data sets, the different ways of clustering will result in different clustering. The different ways of defining distances will result in different clustering results. Okay, and this algorithm also has its own pros and cons. Okay, so compared to k-means, it is, more informative, okay, because it returns a hierarchical structure among the data points, and you can use that data structure. You can use that structure to decide which threshold you choose to use. Okay, you can decide how many clusters by basically moving a threshold up and down. Okay, it's easier to get a interpretable result. But also, its cons is there. It's very slow to compute. Okay, its time complexity basically is big O of n cube. It's like, and also makes sense, right? You want to maintain the distances between all the available clusters, right? You want to use some data structure to store the distances among all possible pairs of the existing clusters. And after some two clusters are merged, you need to update that data structure, right? Because the distance has been, there are two clusters are removed and a new cluster are inserted, and the distance between all the other clusters to that newly added cluster needs to be updated, needs to be computed and updated, right? So it's a very slow algorithm to run, and it's also sensitive to outliers, okay, because it tries to connect all the data points, okay. And it does solve the some of the convex, non-convex shape distribution. Okay, for example, the one below. Okay, it will classify the bottom up one as the upside down one with different the curves with different clusters, but somehow it didn't recognize the two rings yet. Okay, so that also indicates there's some space for improvement, some space to explore new clustering algorithms. Okay, so that's hierarchical clustering. And then let's look at the next one. Let's look at the so-called density-based clustering. Okay, and the idea behind is that only using the distance is not enough, is not sufficient to determine whether 2 points are connected. Okay, but we will need to use finer information, like a more fine-grained information, which is the density. Okay, and the density is basically how many data points are nearby within a certain region, right? And we will use that information to decide whether we should connect data points together. Okay, generally speaking, we will only consider the densely connected data points. They form a cluster. If the data point is very sparsely distributed from each other, then we should basically not consider them as a one cluster. All right, so it is the DBSCAN algorithm within this family of cluster algorithms that we will look at. Okay, so we'll look into some of the technical terms here. The DBSCAN will assign several roles to the data points, to each data point. Okay, there will be the so-called core points. Okay, and from the core points, there will be reachable points and outliers, or you can call them noise data points. Okay, and the core points will be decided by some threshold. Okay, and this threshold is, in this case, it's the minimal points. Okay, so it's the minimal number of points that are within a distance. Okay, the distance is a kind of a radius. Okay, epsilon. Okay, so if there are at least the minimal points, neighboring data points are within the region of within the distance epsilon, then we say that data points at the center is a core point. So this is a very straightforward definition, right? And then if another data point Q is directly reachable from P, if Q is within the distance, right? That is also a straightforward definition. We are using this epsilon as a way to define a radius, right, of reachable distance. So if we use a series of reachable data points, like say from P1 to Pn, we basically can define a path, right? So if we can reach from P1 to P2 and P2 to PQ to P3 and so on until Pn, then we say that the Pn is reachable from P1 because all the adjacent data points along this path, they are reachable. Okay, and if there are some data points that are not reachable from any other data points, then we can consider them as outliers. All right, so in this particular case, if you look at the data points here, P, right, it's basically a core point, right? And Q, it's not a core point, but Q is indirectly reachable from P, because if you like, you can reach from P to this data point and this data point and this data point, while this data point is within epsilon, within the epsilon region of P, right? All right, so let's see what DBSCAN can achieve in the data set. Okay, all right, so here we have a pretty simple example of how the DBSCAN can run on the minimal toy data sets. Okay, so if here is not example again yet. So if we define the minimal points to be 4, then all the red points here are core points, okay, because they are reachable from one another, and they can form a single cluster. So if we put all the red data points together, they can form a single cluster. And if you look at the B and C, they are not core points, but they are reachable from A. So they also belong to this cluster, right? But if you look at the N, then since it's not reachable to any data points, so it is considered as a outlier and an outlier. Okay. So from the next slides, we have a stepwise showcase of one example. Okay. Yeah, so we will basically, the DBSCAN will first find the points in the neighborhoods for every point and identify the core points, right? So it will basically scan all the data points and compute the distance from that data points to all the other data points, and then use that epsilon to determine whether it should be considered as a course, okay? And then it will find the connected components, which is using some graph algorithms of the core points, and then ignore all the non-core points, okay? And for each non-core points to a nearby cluster, it will examine whether it is reachable from a nearby cluster. If so, it will be assigned to that cluster. Otherwise, it will be also considered as a noise. Okay. And let's see this small breakdown example here. Let's use the minimum points as 3. Okay, so if there are more than 3 numbers as neighboring in the neighbor area, then we say that point is a core data point. Okay, so in this example, P1 is a core, right? So we should create a new cluster. And all the 4 neighbor points become a candidates to expand. Like, for example, we could expand from P1 to P2, right? And we add P2 to that cluster number 1. Okay, and we find a new candidate P3. And then new P3 is also added to number 1, and we found a new neighbor P4, but now it cannot be a candidate because P3 is not a core point, because within the region of P3 there are only 2 points, right? So P3 is not a core data point. Okay, and then we should just expand towards the other direction. Okay, and P1 is added, and P6 is added, and the new candidate P7 is found, and P8 is found, but no new candidate is found. Okay, and P9 is found, and the P10 is also found. Okay, and we will stop expanding at this case, and the P11 will be marked as basically a noise data points. Okay, because P11 is not reachable from any core data points. So the final output will look like this. So it's basically that the trend is that all the data points that are densely connected, okay, that are have a very dense spatial distribution, it will be clustered as one group. Okay, so that is basically how it works. And the pros is that it's very fast, pretty fast. Okay, time complexity can be optimized. Okay, and it's also works pretty well on finding the arbitrary shapes in clusters, and it's all very robust to outliers. Okay, because it will use the density, use the minimal points and the distance epsilon to define the outliers. Okay, so it also has its own cons, because sometimes within one data set, some part of the data points may be more densely clustered compared to other parts, right? But they are still 2 clusters. Okay, so if within some region, the data points are very close toward each other and it's very densely clustered, while the other data points are more, loosely clustered, right? So in that case, the algorithm will often, consider that loosely clustered data points as outliers, but they're actually supposed to be considered as a second cluster. Okay, so that is because there's only one parameter, only one minimal point parameter for one run of the algorithm. Okay, so the original version of it is not able to deal with that problem, but I think there should be some improvements of the algorithm itself. Okay, yeah, and sometimes to choose the distance threshold, it can be difficult, right? And the good news is that if we look at the 2 rings, it's correctly, basically as we expected, they cluster in a way that we expected, that makes sense from the perspective of connectivity, right? Because all the inner rings, they are more densely connected towards each other, while the outside ring is should itself be another cluster. And if you can notice, the running time, it's pretty fast as compared to the previous hierarchical clustering. Okay, hierarchical will take like almost 0.3 seconds on these data sets, while this one only takes like 0.01 seconds. So which is way more faster than the hierarchical clustering. All right, so yeah, that's pretty much for the two clustering algorithms, hierarchical clustering and density clustering, that we should talk about today. And let's talk about let me stop the video recording for now.